So today we'll talk about how to apply transformers to time series. So last week, we talked about how to apply RNNs or recurrent neural networks to time series. So if you don't know about transformers, basically, if you think about ChatGPT or all those language models, they all use transformers instead of recurrent neural networks. So we want to see if transformers can bring the same kind of advantage to time series. So as a recap, DPR is an RNN-based model. So at every step, we make a prediction. And in the case of DPR, it will be some parameters which you use to parameterize the distribution. So it can be a Gaussian distribution where you're predicting one number for mu and one number for sigma at every time step. And you're making predictions for each time step sequentially. So, for example, if we are at um, time step t, then you will have to make predictions for time step one all the way to time step t minus one. And you'll base your prediction for time step t on all your previous predictions. And I think we mentioned last time, this will, in some cases, lead to the accumulation of error as we do those recursive computations. So if you have a chance to read the DPAR paper, this is the notations that they use in your paper. So Z will stand for the target variables, X will be the time-dependent covariates, and S will be the static covariates. So static means that it doesn't change over time, which can be which country the time series is coming from, or which geographic location time series coming from. So there are several issues with RNNs. So most notably, it's not very scalable if we have a lot of compute power. So if we have a very large RNN, it will first have the exploding and vanishing gradient problems that we talked about earlier. And also because doing both training and prediction, you have to update this memory vector as we traverse over time. This means that you are kind of limited to having this for loop for both your training and inference time in order to update this memory vector. And second issue is that in order to pass some information from time step 0 to time step t plus 1, you have to go through all those t time steps. So this is you have to store all those information in this fixed size memory vector. And this is probably very hard to do because our memory vector is very limited in size. And it's very hard to decide what kind of information you want to keep inside the memory vector. So this corresponds to the information path length problem. So the main advantage of the transformer model is that instead of having an information path length of t, which is the length of the window, the size of the window in this case, it changes to just a constant one. And also for both training and inference, we can simply do it in parallel. So we essentially want to get rid of this memory vector and have some other kind of mechanism to look back. And because we got rid of this training and inference speed limitation, it makes transformers much more scalable. So let's first look at how attention works. So here, instead of having feature vectors, you can think of each of those circles at the top being one time step. So here 0 will be 7 time steps. And in order to compute the 8th time step, you can dynamically look back at the previous 7 time steps and see which time step you want to focus on. So maybe the thickness of the line here indicates which time steps are more important. In this case, maybe the second time step and the last time step are more important. And you want to represent the 8th time step as a weighted sum of all the previous time steps. So this is a high-level idea. And intuitively, given the target vector, because when we compute the predictions for the 8th time step, we will start with some kind of vector. And given this vector, we can compare its similarity with each of the previous time steps. So for each of the previous time steps, we'll also get a vector representation for all its features at that time step. So given those two vectors, or given the 8th time step vector, we'll compare its similarity with all the previous vectors. And we do it via this dot product. And this, if you scale it, so dot product will give us a scalar, and in this case, we'll end up having 7 scalars. And if we rescale those 7 scalars, we can kind of renormalize it into a probability distribution so that it sums to 1. And then we can just take the weighted sum of all those previous vectors as our target vector. So one way to think of this attention mechanism is it's kind of like a linear layer where all the weights are adjusted dynamically depending on the input. Okay, and now let's take a closer look. So given this feature vector at every time step, we'll process it with 3 different linear layers. So the first linear layer will process into a query vector, and then the key vector as well as a value vector. So this is very similar to the concept of a dictionary in Python. So suppose we are still trying to compute the 8th time step, then we will use a query from the 8th time step and compare it with the keys from all the previous time steps. So we'll take this query and compare its dot product with the key from the first time step, second time step, and so on all the way to the 8th time step. So one thing to know here is that the vector at the 8th time step can actually attend to the vector at the 8th time step. So it can attend to itself. And having this q times k will give us this dot product. So will give us a scalar. So the softmax is how we convert this series of numbers. So suppose, let's look at the figure at the bottom. So given this vector, we can compute.
To add contact information for before I.
Sorry. We can rebalance this vector of scalars into a probability distribution. So the input will be one number for each class, and the output will be the probability that correspond to each class. And then given this probability or the weight for each time step, we can combine it with the corresponding value vector from that time step. At the end, we'll get this Z as our final representation for the updated representation for this time step from step 8. So if we compute, another thing to note here is that this linear layer will actually be shared across all the time steps. So if we're working with time steps 8, we're using these 3 linear layers. And if we are working with time step 10, we are still using the same set of those 3 linear layers. So in a sense, the size of input is independent of the number of parameters in the attention layer is independent of the size of input. So maybe you can process a very long window, and you can still only use the same 3 linear layers, so weights don't get larger over time. And one set of those 3 linear layers is called one attention head. And you can actually have multiples of those attention heads. So you can maybe have 4 sets of those 3 layers. So once on a high level, maybe one set of those attention heads can be thought of as focusing on one set of features. So you have multiple heads. I mean, maybe you can dedicate them to focus on different sets of features. So if we look at this window on the left, this corresponds to the, I think it's hourly occupancy rate of a time series. And we can look at the attention map, the learned attention map on the right. So we see that the model always pays a lot of attention on the diagonal line, which means that the time step is attending to itself. And each of the peak, so if we look at a straight line here vertically, then right below this line, 24 time steps below this line, we see another bright area. This corresponds to probably the peak that it's attending to. So maybe here at this peak is attending to all the previous peaks. And maybe as the smaller peak here is tending to the previous smaller peaks. Because there's a strong domination of the reoccurring period of 24, then you can see this recurring pattern in the attention map as well. And it's also interesting to look at the weekends. So you see that if we are here on Saturday or Sunday, it's actually not being attended to by all the weekdays. And a good way to add this kind of interpretability to transformers is by just plotting out its attention map and see what the attention map looks like, or what kind of patterns the attention is attending to. So what we talk about is this self-attention, the self-attention section here. And so let's then take a look at how a transformer block works with this self-attention mechanism. So given this vector at each time step, we first go through this self-attention, and then there's also a residual connection that skips this self-attention part and just add it to the results after the self-attention. So there's like a shortcut indicated by this dash line. And one thing to note here is that when you apply, so here we are actually talking about, so recall that previously we said there are 2 ways to do predictions for time series. So there's one method of doing direct prediction where I directly predict everything the entire forecast horizon altogether. And the second method is we can just predict one step at a time and recursively fill up our forecast horizon. So if we're using the direct forecasting method, now the target variable and the covariates can come from the same time step instead of like dpar, which is here. So the z will correspond to the target variable from previous time step. So we do this only to make sure that we can do direct forecasting as an inference time to fill up our forecast horizon at once instead of recursively. And this feed-forward layer is just two linear layers. And then there's also a residual connection that allows the transformer to bypass this two linear layers and just do the add and normalize. And the last thing in this transformer block is this positional embedding. What it means is that, so for RNNs, as we iterate through the time steps, it kind of give the model a sense of which time steps are further away and which time steps are more recent. But for transformers, because we're directly doing this attention mechanism, so we're directly computing all those edges, we kind of lost the information of which time step this feature vector is coming from and which time step is more recent compared to the other time steps. So we add that back through this positional embedding. So the way the original transformer paper had this positional embedding is through the sine cosine waves. So here it's trying to generate a feature vector of length 4 for this positional embedding. And it generates this sine cosine wave of different frequencies. So that's first, so the x-axis will correspond to the different time steps. So the first time step will be looking at this first dot on each of the four graphs. So the first number will be 0, and then 1, then 0, then 1, if we look at the 4 graphs vertically. So this 0, 1, 0, 1 will be the positional embedding or the positional encoding for our first time step. And second time step will be 0 0.8, 0 0.6, 0 0.6, 0 0.8. And third time step will be so 0 0.9, negative 0 0.4, 1, and then 0 0.2. So at each time step, we'll get this feature vector of size 4, which represents our positioning information. And surprisingly, this kind of information is already enough for transformer to figure out which time steps are more recent or which time steps are further away. And you can actually choose different kind of frequencies. So if you set the hyperparameter d to 50, then you can choose some kind of frequency. And if you set it to 20, if we look at the third plot here, it's a frequency, each period is actually longer than if we set it to 50. Okay, and now let's look at how the transformer block can actually be applied to do time series forecasting. So same as before, we have a period of observed history and another period of forecast horizon. So each time step will get this feature vector. we can first add its positional embeddings and then go through the transformer blocks. So there can be multiple transformer blocks. If we think about the encoder and decoder perspective, then we can take the representation from the last layer of this encoder and then another difference between just the encoder transformer block versus a decoder transformer block is that in the decoder block, we not only need to do self-attention, which means that we every time step in the forecast horizon attend to every other time step in the forecast horizon. We also do this encoder-decoder attention, which allows each time step in the forecast horizon to attend to each time step in the observed history. So this corresponds to the encoder-decoder attention. So we take the last layer, the outputs from last layer in the encoder block as the inputs or just as the keys and values for this encoder-decoder attention. And everything else will remain the same. And the output embedding from the last decoder block, we can process each time step separately using this shared linear layer into the actual predictions for target variables. So because right here in this picture, we are trying to do the direct forecasting method, instead of having the target variables which are missing in the forecast horizon. For those missing target variables, we'll just pad them with zeros. So actually, you don't have to pad them with zeros. You can actually pad them with any arbitrary numbers. And the transformer will figure out that it will need to fill those missing zeros at the forecasting time. So the trainable weights will be this linear layer for the query, key, and values in the attention layer. And also the linear layers, the two linear layers in the feed-forward section. And this will be our trainable weights in the feed-forward, in each of the transformer blocks. And again, it's the size of those weights is independent from how long your input sequence is. And alternative to this directive forecasting method, you can still use the iterative forecasting method. So at the decoder time, you can just predict one time step at once and then use your prediction as input to a next time step to do your next prediction and so on. So in that, if you're doing that, then your target variable will be your prediction from previous time step. And as a recap, direct methods will be better if we're doing long-term forecasting. So if your forecast horizon is very long. And iterative methods will allow you to predict a different forecast horizon than at your training time. So maybe at training time, you only train it to predict 24 time steps. But at test time, maybe you want to predict 48 time steps. You can still do that. And there are some challenges with the vanilla transformer model. So first, if we look at just one time step in the attention mechanism, if we just represent each time step as a separate feature vector, then it's very hard to for the attention mechanism to figure out which steps to look at. So if we look at the plot on the left, maybe the two red dots here, the transformer might think they're very similar because they're of the same height. But if we look at, but from our perspective, we know that the second dot is actually more similar to the last section here because they share the same pattern. So if we look at the peak on the right, we see that the smaller peak actually looks very similar to the larger peak at the end. So instead of just comparing one time step at a time, maybe we should compare multiple time steps at a time in the attention mechanism. And the second issue is that if we just directly apply the attention mechanism, then we have a very high memory cost. So because when we calculate attention, the memory cost will be L squared, where L it will be the size of our time series window. So maybe some ways to reduce that will be just randomly choose a subset of the attention or sorry, choose a subset of the time steps to focus on in your attention mechanism. And in the future meetings, we'll talk about some better methods to deal with those two problems. And if you're interested, you can look at those future further readings at your own time.